Hello, my name is Adrian, and today I'm going to present our work introducing multi-level feature distillation of joint teachers trained on distinct image datasets. This paper represents a shared work together with my supervisors, Professor Bogdan Alexe and Professor Radu Ionescu. We will start by introducing our motivation. The standard paradigm in machine learning is to train a model on a single dataset, and we expect that model to be able to generalize to new samples. We are interested in increasing the generalization ability of models across different datasets. Currently, in computer vision, no dataset can capture the entire variability of the world, and recent research shows that each dataset comes with an implicit bias. Our goal from this paper is to reduce the implicit bias, improve generalization across datasets, and increase task performance at no additional costs. For that, we proposed multi-level feature distillation of joint teachers, MLFD in short, representing a new teacher-student framework that fuses knowledge from multiple teachers into a joint architecture used further for distillation. We validate our method on 7 image classification benchmarks, 3 action recognition experiments, and various ablation studies. The MLFD framework uses 3 stages. The first one is optional, represented by training one teacher on each dataset. We can replace this step by using pre-trained or foundation models. In the second stage, we merge the individual teachers at a certain representational level into a joint teacher. The joint teacher comprises the remaining representational levels. Finally, each student trains with multi-level feature distillation from the joint teacher. The joint representation embeddings. We use concatenation for the embeddings returned by the individual teachers, and we apply adapter blocks to bring the features from a certain level to the same spatial dimension. We created the architecture of the joint teacher from repeated neural network blocks that can vary from simple dense layers or pointwise convolutions to more complex layers like transformers or convex blocks. The loss function for multi-level distillation uses 3 terms: a cross-entropy term between the ground truth and probabilities predicted by the student, another cross-entropy term between the class probabilities returned by the joint teacher and those of the student, and finally, the mean squared error at a certain representational level between the feature map of the joint teacher and the feature map of the student. We evaluate our method on 3 sets of models, 2 for image classification and 1 for video action recognition. We have T1, the set of POC models used for proof of concept experiments, and the T2, which uses state-of-the-art architectures composed of modern convolutional networks, transformers, and hybrid models. As baselines, we start from each initial individual teacher and move towards multi-dataset methods, such as multi-head models with a single shared backbone using independent prediction heads, and the second approach, the joint head model with a single classification head containing the total number of classes. As you can observe, students and teachers using the MLFD method surpass all 3 baselines. Using our method, each student performs better than the teacher throughout the optimization process. You use the same hyperparameters and training budget between experiments to conclude the performance gains using our method. Our method produced better results also on the state-of-the-art models, even when the joint teacher mixes information between convolutional and transformer architectures. We compared our framework to other distillation methods and obtained better results. The other distillation methods are single dataset methods. Thus, we can conclude that the multi-dataset approach helps. We start with pre-trained individual teachers on Kinetics 400 for the action recognition experiments. By our joint teacher approach, we obtain significant performance gains regarding top 1 accuracy and mean average precision. We also conducted multiple ablation studies to understand our method better. The first being which distillation level is more beneficial for our distillation. As expected, we observed that the performance of the joint teacher decreases when using higher levels of representations. We continue to study the effect of increasing the number of datasets for our method. As of now, increasing the number of datasets has resulted in positive results. We studied the impact of having different datasets in an experiment where our framework is performed only on a single dataset. In conclusion, having multiple datasets improves our method. We observed that applying our method to a single model architecture also works, leading to better results than the dataset-specific models. To address our initial claim about the generalization ability, we perform an ablation study where the joint teacher trains on representation from 3 different datasets than the one used by the student. In this case, our method also surpasses the initial model results. To inspect and visualize differences between models, we applied Disney projections to the final embedding layer of the models. We can observe that models using our method have more separable 2D projections of the embedding space. Thank you for listening. Our code is publicly available on GitHub. If you have any questions, feel free to ask them during our postal presentation.